Hi there and welcome back to Algebra 1 Workbook, where we are now on Chapter 6 and we're discussing exponents. Well, that's sort of a wacky little in there. Okay, so what is an exponent? Well, an exponent visually looks like a particular number raised to a certain power, right? We call this the base, and we call this the exponent. And what it means, practically, if, say, we were raising 2 to the 4th power, is that we are multiplying 2 times itself, that exponent amount of times, so 4 times, right? In number of times. So if I were to express this, would be x times x to whatever the n number, right? To the n factor of x, whatever that is. Okay, so exponents are a lot of fun. Exponential expressions have some tricks, some things that might fool you a little bit, and I really want to concentrate on those. So if I have something raised like 2 to the 4th power, and I have a negative on the outside, that's different than if I enclose that negative in the 2 together. Now the difference is this. Here the first one I'm saying negative on the outside, but that 4 only applies to the 2. Right? So my outcome is very different, whereas here I'm saying take that negative 2, whatever's encompassed in the parentheses, and multiply that by itself 4 times. Now, just looking at the signs, do you see what happens here? This answer is negative, and because there are 1, 2, 3, 4, this answer is positive. Right? So 2 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. So our answer here is a negative 32. Here it is a positive 32. And that's a significant difference in the middle of a complex operation, right? When we have an equation where we have several signed numbers and several of them are being raised to various powers within multiple operations. All right. Another thing we should talk about is that how you say particular exponents. This can be, we can say x squared or x to the 2nd power. This is x cubed or x to the 3rd power. This is just x to the 4th power, x to the 5th power, and it continues 6th, 7th, 8th, 9th, whatever it is. So the other ones that have little nicknames are the squared and the cubed. Now, exponents do fall in our order of operations, right? We talked about that before. PEMDAS. So it's right here. We had the parentheses, which recall we talked about all the different enclosures that this little p here seems to represent. Now the exponent, the e here, it does include exponents of whatever value. Anything that you see raised to any power will need to be solved before you can move to multiplication or division or addition and subtraction in your problem. But this E also represents roots, okay, and we will talk about that in the next chapter. In this chapter, we also want to cover the idea that anything raised to the 0 power equals 1. And it doesn't matter what it is. If it's raised to the 2nd power, if it's raised to the 0 power, the answer is 1. Of course, this does not apply to 0 being raised to 0 power. That's something that is also undefined, and it really has no meaning. You can take nothing and multiply it 0 times itself. It doesn't mean anything. Okay, so don't say that equals 0, because it doesn't. It has absolutely no meaning. It's undefined. Another very basic rule is that if we have an exponent that's being raised to a negative power, we have to deal with that because it's not in its simplest form. To understand it, we have to toss that value with the exponent into the denominator. And then we don't have a negative anymore. And now we can use 1 over whatever the value is that's being raised to that power and further simplify it. So when you're asked to simplify an expression or an equation and you have a negative exponent, you're not done. You need to keep going until that is expressed in non-negative exponents. Some instructions will clearly say, express all answers with positive exponents. But you should assume that unless it says not to. So some examples of this: if you have 2 raised to the 4th power, and that 4th power is negative, 2 to the negative 4th power, then you have, this is your next step. And then, just like we did over here, 2 to the 4th power is 32, but it's in the denominator. 1 over 32 is your final answer, simplified as much as possible. So we can also sometimes have problems where the negative is on the outside of a parenthesis. And if we have multiple terms, especially, something like this with a fraction form, where let's go ahead and fill this in. Let's say we have 2/3, and the entire thing is being raised to a negative. Let's just use a negative squared. And the first thing that we need to remember is that we need to deal with the negative first. Whatever's on the outside of that parenthesis, that exponent, in our order of operations has to be considered first. What this functionally does is completely flip the fraction, right? And then that negative is gone. So think about this. What's happening, right? The x goes to the denominator. Here, the 2 goes to the denominator, and 3 moves to the numerator. And that makes it a positive exponent. So now, this exponent of 2 needs to be distributed to both the numerator and the denominator. Essentially what we have in the next step is this. Three times 3 9. 2 times 2 is 4. This cannot be simplified any further. So that's our final answer. Inversely, if we're given something in fraction form that perhaps has a particular exponent, negative exponent, let's make this functional. Let's say you have a 3 and a negative 2 up here, and you have a 2 also to the negative second power. Well, in the numerator that's being raised to the second power, that means that I need to put that in the denominator, right? So now I have this, and that denominator of 2 raised to the negative second power needs to move to the numerator. Okay, then I have this as my answer. Simplified as much as possible. So now we want to think about what happens when that exponent is a fraction. We looked at it as positive, we looked at it as negative, and now let's look at it as a fraction. Essentially, what this translates to is this. There is a known inverse relationship between exponents and roots. So as long as this is a real number, x is a real number, and n is a positive integer, right, that denominator in the exponent, then this is true. This holds true. Let's look at it as an example here. If I have, let me give something that I might be able to solve here. Let's use 9, where I have over, it's being raised to the 1/2 power. Essentially what that means is this, you see this n, how it's now the index? Well, even though we don't generally write square roots, the 2 up there, I'm going to go ahead and do that just so you can see where that 2 goes. And then 9 goes there. These are equivalent statements. Then I can consider the square root of 9, which is 3. This is a really foundational relationship between square roots and exponents. So let's do another example of that. Even if I am raising a fraction, the entire thing, to a fractional power. And let's raise it to the 1/3 power. So whatever's on the outside of the parentheses, that exponent has to be distributed to both the numerator and the denominator. So your next step, at least in thought, but you should write it down until you can operate it in thought very clearly, is that you're raising 8 to the 1/3 and you're raising 27 to the 1/3. Then you can take a look at what we did previously, where that 3 becomes the index and that 8 is the base. Still the base. Same thing happens down here. That 3 in the 1/3 becomes the index, and the 27 is the base. Now we can think about what is the cube root of 8. Well, that's 2. And the cube root of 27 is 3. And that fraction will not reduce any further. So we're done. Now to further complicate things, if I have a value, say 100, and I'm raising that value to a particular power, maybe we should do 1,000 so that I can do this. So let's say I'm raising it to 2/3. What we have to know is that x, when it's raised to a particular value over the nth, remember that n, when we put it in a radical form, in a root form, that's the index, right? We can also extract either the m or the n and sort of pull it apart. It's almost like factoring out a value where we could have 1 over n here, and that m is out here. Because what do? When we are raising a value to a power, we are absolutely just multiplying those powers. Okay? So, if I multiplied, so here's my little thought. Okay? If I multiply 1 over n times m, I get m over n. And that's exactly what's here. That's what we started with. So I'm factoring out that m. Okay. So I want to do that over here with my 1,000 being raised to the 2/3. And my next step would then be to factor out the 2, which is in the numerator, and that will leave me with the 3. And then I have the 2. Now we want to apply that inverse relationship that we talked about with exponents and square roots. That 3 in the denominator is an n that is the equivalent to the index here. So let's just do this. That 2 will remain on the outside. So the entire value will be raised to the second power. Our base is still 1,000. And so this becomes the cube root of 1,000 is 10. 10 times 10 is 100. 100 times 10 is 1,000. You can count the zeros if you don't believe me. Now we still have the second power. 10 times 10 is 100. And that is our final answer. Now we can even have exponents that are raised to a negative power, right? Within all of this. So we have a fraction and a negative power. We can put it all together. For example, let's see here. Negative 2/3. All right. So dealing with that negative first is a great place to start. So that means that 27 needs to be placed into the denominator of a fraction in order for it to not be negative. We have the 2/3. So now remember that we want to sort of factor out that numerator, the 2. And I'm going to just show every step, although once you do this enough times, you likely won't be writing this step. You have the 1/3 inside being raised to the 2nd power. Now what? I hope you remember. Now we can show the cube root. The base is the same, raised to the 2nd power. Do you remember what the cube root of 27 is? So it's 3. And remember, that's still being raised to the 2nd power. 3 times 3 is 9. And now we have the solution. And look where we began. We had basically 27 to the negative 2/3 power equals 1/9. All right, so now review of all these rules for exponents that you really have to commit to memory. Whenever we have an exponential value that we're multiplying times another exponential value, that means we are adding them. Adding the exponent. For example, if we have 5 to the 2nd power times 5 to the 3rd power, that's like saying, whoops, not x, 5 raised to the 2 plus 3 power. That's 5 to the 5th power. 5 times 5 times 5 times 5 times 5. And that winds up being a rather not large number, so sometimes you'll be asked to simplify the exponent and you'll leave it like that. If you are asked to solve, then this is your answer. So when we multiply exponents, we are really adding them. So if we're adding them when we multiply, what happens when we divide them? Well, would have to be the inverse. We have to subtract. So if I have 5 to the 3rd over 5 to the 2nd, essentially that's 5 to the 3 minus 2 power, which leaves me with 1. And we really don't write the 1, but that's just 5. Okay, when we multiply, we add. When we divide, we subtract. Let's keep it going. When we raise a power to another power, we'll go ahead and use what the book uses, p there. Then we are multiplying. We're basically saying m times p. So what does this look like? 4 with the power 2 times the power 3. So we have 2 times 3 is 6. So we have 4 to the 6th power. And again, that's a rather large number. Another useful rule that we have is whenever we are multiplying something inside a parenthesis and then raising it to a particular power, we can show that base being multiplied, oops, that should be a y, with the individual exponents for each of the bases. So practically speaking, if I have, say, a 2y, and I want to raise those to the second power, I have 2 to the second power times y to the second power. What this looks like is 4. I don't know why I put that 2 on the outside, but it doesn't matter. Okay, and of course, that's the same as this. All right. Now, final rule, kind of a quotient rule with the exponent. So we have x over y, and very similarly to the one that we just did, when you have an exponent on the outside, let's just leave this p for now, you can distribute it to the numerator and the denominator values. Now, in a practical problem that looks like this, it just means that I'm doing this. So these are very important exponent rules that you will be using throughout all of your algebra equations from this point on moving forward, and really you have to memorize them. So this concludes this chapter. I know it's a lot of information. Watch it as many times as you need to. Make sure you can complete successfully all of the exercises in all 6 sections of this chapter.